Good morning or afternoon, maybe even evening for physics. This is a fourth day in the last unit, modern physics, and we're going to look at half-life today and how you measure radioactive activity. And basically, we'll be looking at an exponential equation if you've taken your pre-cal maths. It'll be an exponential equation. So it'll be similar to that if you've taken pre-cal already. And we'll be looking at half-life of radioactive isotopes. Okay. We'll wait for the board to pop open here and we'll outline what we'll look at today. Okay, so let's go ahead and pop this one open. This is day 4 in unit 4. And this is, we're going to look at half-life of radioactive isotopes. Okay. In terms of what we're going to be looking at here, is we're going to be looking at the general equation of that, and we're going to be looking at how to do exponential equations if you haven't done it before. We're going to be looking at the definition as well of half-life. And we're going to do some examples in here. So let's get started with the basics first. So if you're thinking about what we're talking about when we talk about half-life, half-life means is the time it takes for a radioactive isotope sample to decay to half its original mass. And that's what half-life means. So, and that is actually an exponential equation and half-life can be quite different as well. And we'll talk about that in a minute. So usually half-life is measured in activity. So let's actually do this. So let's start off with example. C14, its half-life is 5,730 years. So decaying rather slowly. But if we take polonium-214, its half-life is 0.00016 seconds. So these things can vary quite a bit, okay? The carbon-14, we use that in carbon dating. Polonium is a highly radioactive element, polonium-214, radioactive element. Okay, and the measurement of decay that we're going to use of radioactive decay is a becquerel. and it's BQ is the symbol for it. And it's 1 decay, per second. But it equals 1 becquerel equals 1 decay. So if I say it's decaying 240 becquerels it's decaying 240 particles every second, radioactive particles. Okay? And if we look at the activity graph, typically of a radioactive element, okay, so if we say, okay, this is, let's use a straight line here. If we say that this part here on the horizontal is our time and the vertical is our activity in radioactive particles, number of radioactive particles, or becquerels, if you like that unit, which is a pretty good unit. So we call this one, let's go to marker here. This is time. And this is activity. And usually measured in becquerels. This could be measured in seconds, years, or whatever, it doesn't matter. And it usually goes kind of like in a decay, an exponential decay. Oh, sorry, this thing's gonna, there we go. Let me draw that again. It kind of froze on me there for a second. Okay, so it's a decay. Starts up here. And it goes all the way down to here without touching. Okay, so this is exponential decay. Okay, so it has an exponential. Okay, so the first half-life would occur, so if halfway down, this would be the first half-life. Okay, once it's half of that, second half-life. And etc. Keep on getting half and half the amount. Okay, time would be equal, but each time this would be chopping down. Okay, so the half-life equation is an exponential equation. So according to what we want to look at today, we want to look at the general equation. Okay, we've got the basic definition of half-life. We want to look at the basic general equation now. And it's just dealing with 2 or half, if you like, because it's going to be using half as our exponential decay. Remember that with exponential equations, if something is greater than 1, a whole number, you get exponential growth. If something is between 0 and 1, you get exponential decay. And that's what we have, because our decay constant is going to be 1/2. So if we say that N0 is going to be the number of radioactive particles okay, usually measured in becquerels, and that N number of radioactive particles in the original sample, sorry, I forgot to put the original sample, sample, okay, and that N is the number of radioactive particles in the future sample. So after some time has occurred. And we're going to say that the general equation, I don't like the fat writing, the general half-life equation is going to be like this. Okay? The future sample equals the original sample multiplied by 1/2 to the power of n. Okay, and you have to make sure that you do the 1/2 to the power of n first because it's exponents, order of operations. So I like to put it in like this. Okay, to remind everybody that you have to do that part first. You don't need the brackets in all likelihood. And this little n is equal to the number of half-lives that have occurred. Oh, just one R. What am I doing? Okay, that have occurred. So n, little n, equals time divided by the half-life of the element. Or of the, I guess we should say isotope. Because it might be a compound or an element too, like uranium-235. Okay? So there are two equations really. There's one for little n and there's one for general decay. So the best thing for us to do is just kind of look at a couple examples. Now, I'm going to teach you how to use your calculator properly to do exponential equations. For doing exponential equations, if we've done what we've done in our past, if we have in our history the use of logs, we can use logs in this. But if you don't know logs, you're going to have to do guess and check. Okay, so that's up to where you are in your math. This is grade 12. Not everybody in physics 30 has pre-cal 30. I'm thinking maybe you all do. I'm hoping you all do. And if you do, you can use logs and you don't have to do guess and checking. Okay, but if you don't know logs, you have to do guess and check for some of the types of examples that we're going to do. Okay, so these are our general equations. Let's look at some examples. So the first example we're going to do is very simple. Okay, let's say the half-life of a radioactive isotope is 2.5 years. Okay. The activity of the original sample, let's say of a sample, is 3.25 times 10 to the 3 Becquerels. Okay, so we got to put that 3 up there as an exponent. There we are. Okay. What would the activity be after 32 years? And we can also do this with mass as well, and I'll show you an example of that. Question mark. Okay, so let's go ahead and set this up. So what do we know is what we're really have to start with. So we know what the original activity is. The future activity we don't know. We want to know what the future activity is after 32 years. So that's what we're trying to find. So if we take our equation here and we say, well, the future activity Y, and you go skinny there. Okay, the future activity is unknown. The original activity is equal to, well, we can write that as a number. That would be 3,250 or 3.25 times 10 to the third becquerels. Okay, and we know that the half-life of this particular element is equal to 32 years, or not 32 years, 2.5 years, 32 years of time. Pardon me. 2.5 years. And our time that we want to look at the future is 32 years in the future. So n, our first little bit, n is time over half-life. So this is going to be 32 years of time divided by 2.5 years per half-life. So this is going to give us 12.8 half-lives. So then we can just apply the formula straight up with this one here. So n equals n0 times 1/2 to the power of little n. We don't need that square brackets because you should remember that it's always what we would say, it's always considered to be order of operations, but I put it in there because people always forget a lot, including me sometimes. Okay, so n equals the original one times 1/2 to the power of 12.8. So you got to do this first. On your button of the calculator, your calculator raised to the power button is usually y, x like this, and some of them are like this. Now this is the exponent button, scientific notation button. Those are different. This button is not times. This is on your calculator. It's this button. Or on some other calculators, it's this button. Okay, don't use the multiply sign there because you'll mess it up. Anyways, we don't start with that anyway. We start with 1/2 to the power of 12.8. So you go, first thing you go is 32 divided by 2.5 to get what you have. And it actually works out to exactly 12.8, which is really nice for us. Okay, so then we go from there. Just hang on, I'm going to put out pause here. I got to answer a question here. Sorry about that. Okay, so let's go through the calculation part. So, and I'll show you how it's on the calculator. So we got up to it's 12.8. So what you do then is take 1/2, or you could use 0.5 if you like, depending on how you do it. My calculator works in fractions, but put that in, push your raise to the power button, okay? Put in 12.8 like that. Okay, you get that number if you've done it correctly. Then you go multiply by 3.25 scientific notation, which gives me an E like that on my calculator, 3 equal sign. And you get 0. Oh, I screwed it up. I put 0.32. Sorry, let me do that again. There we go. 0.455. So if we rounded that off to n is equal to 0.46 becquerels. So it's not even doing one Brickell, it's doing one Brickell every 2 seconds or radioactive. That would be our result. So that's easy when you're trying to find the N. Okay. Where it gets a little more tricky is when you're trying to find the little n value. Okay, we can also do one with n0 as well. We'll do an example like that as well. Let's do 3 examples here. Let's check my time here. 20 minutes, yes. Easily we can do the 3 different kinds of examples today. Okay, just hang on here. Pause it. Okay, so sorry about that again. So let's go ahead and do another one here. Let's flip ahead and let's do one where we're going to do an example of another type one. Let's get to the right spot here. Oops, wrong one there. Okay, so let's do an example this time where we're doing the original sample given a future sample. Okay, and then we'll do one where we're doing the time because those are the most difficult ones. Those are the ones where we have to use logs. Okay, so let's go ahead and do that. So here's one where we can do, this is be pretty much the same as the last one, but it's a little bit different. So we'll just pop one in. So let's say a radioactive element has a half-life of 4 days. If it decayed to 4.05 grams, okay, so you can also use grams rather than Becquerels, grams of radioactive material. Okay, that's another measurement they use. Right? They don't always use just Becquerels. So if they decayed to 4.05 grams from let's say 19.5 grams, in let's say 90 days, what was the original, or I screwed that one up. Sorry guys. Let me say, if it decayed from 4.05 grams in 90 days, what was its original sample size? Great. Okay, so sorry about that. I was kind of giving you too much information there. We got to calculate one of them. So in this case, first, if we're working this one out, okay, we have the original sample size, N0 is unknown. Its future size was 4.05 grams of radioactive material, so it doesn't always have to be Becquerels. We know the half-life equals 4 days, and we know that the time is equal to 90 days. Okay, so that means if we work this out, little n is equal to 90 over 4, which if we do that on our calculator, doesn't give us a round number, but it gives us 22.5 half-lives. Okay, so that means we're going to have to work backwards. So now when we put the original equation, okay, n equals n0 times 1/2 to the power of little n. Okay, you can have those big brackets to remind you to do this first if you want. It's not needed. So then our future sample what is the original sample size? That one right there. So our future sample is 4.05 grams of radioactive material. This is blank, and we have to calculate 1/2 to the power of 22.5. So go ahead and do that exponent first. So 0.5 to the power of 22.5 equals. Okay, so you get one. I'm going to leave it on my calculator. 1, 2, 3, 4, 5, 6, 7. Okay, so then we're going to have to. Okay, we're going to have to multiply or divide 4.05 by this number that's on the calculator. So we end up getting 24, what is it here? 24 million. So let's go two significant figures. 2.4 times 10 to the 1, 2, 3, 4, 5, 1, 2, 3, 4, 5, 6, 7 grams. So pretty big sample in that question. All right, so those are the easier ones because we're not using logs at all. Now, if you have a log question, if you have to find the time type question, that's where you have to either use guess and check or logs. So let's do an example like that. Those are much more difficult than these ones. And pre-cal 30 people will know how to do the logs, and I'll do a log way, and then I'll show you if you don't know logs what you have to do. You just have to guess and check. Okay, so let's go ahead, and I've got one here on my other side here that I'll pop in for you. Okay, so this one here, let's type it in. Okay, so a 2.5 grams, so I'm not using Berkel's again, I'm using grams, which is fine. Sample of a radioactive element has a half-life of 8.00 days. After some time, the sample has only a mass of 0.580 grams. What period of radioactive material, obviously, what period of time has passed? Okay, so this is where we're going to get into logs and log rules. Okay, pre-cal 30. Okay, so if you have your pre-cal 30, you will know what I'm talking about. Maybe you're taking it presently and you don't know. Maybe you took it in first term and can't remember. So we'll do a refresher. So we're going to be using N equals, that's the future value, it's right there. Okay, it's decayed down after so much time down to 0.580 grams. Originally, it started out at 2.05 grams. The half-life is 8 days. But we can't find the little n, so we have to solve for little n. So we have to use the equation n equals n0 times 1/2 to the power of n. And we have to solve for this one because we know what n and n0 are. 0.580 equals 2.05 1/2 to the power of n. So we divide out the 2.05 on both sides, and we get 0.2829 equals 1/2 to the power of n. Okay, so now at this point, if you don't know logs, you have to now just plug in a bunch of numbers like 1, 2, 3, 4, 5, until you get exactly this number. So 0.5 to the power of 6, 0.5 to the power of 7, 0.5. So if you do that, let's do that, 0.5 to the power of 7. Okay, you end up getting that number, which is way, way, way too small here. right? So then you would have to go, okay, well, maybe 2, 0.5 to the power of 2. Okay, a little bit too small. It's close, but not quite there. So then you'd have to go, okay, it's beyond 2, but it's not past that. Okay, and you'd have to guess your way to it. Okay, but we're going to do it the log way. I'm just going to check to make sure that I get the. So I rounded this off. It's actually 0.2829. Okay, so if you have this equation, you can actually use logs. Now you can log this number, and that's going to equal the log of this number. Okay, now if you know log equations, okay, this is going to stay here. Now with a log equation, when you have a number to there, you can bring it out front. So this is going to be n log 1/2. Okay, which is 0.5 if you like. So now we have an equation to solve for our value. The log of this divided by the log of 1/2 equals n. Now, rounding off will change your answers. So I usually keep this whole number on here. Okay, so let's do that a little bit better than that. Let's go log of 0.2829 divided by log of 0.5 or 1/2 equals n. So take your calculator out. Okay, and you can go, depending on your calculator, I usually go log, and then I put in brackets, because I like to get the exact number. I put in brackets the 0.580 divided by 2.05, and I close the brackets like that, and then I get a number, and then I divide that by the log of 0.5 or 1/2, and I get 1.82. Okay, that's not our time though. So n equals 1.82, and you're like, hey, wasn't 1/2 to the power? See, but what I ended up doing there when we were guessing checking, I think I used 2, not so 1/2. So let's go 1.5 to the power of 1.82. Okay, and just for a double check. Okay, and it worked out. So this is our n value. So that means to find time, we know that n equals time divided by half-life. Okay, so if we want time, we have to multiply this. So time equals n times the half-life. So in our case, it's 1.82 times the value of, what was our half-life? 8 days? So multiply this by 1.82 times 8. 14.56 or 14.6 days. Okay, now if you didn't know logs in this type of example, when you got to here, you would just go 0.5 to the power of 2 and you would guess it out. Well, that makes no sense. Why isn't the guess and check working here? It should be greater than that. Did I make a mistake in my logs? Let me just pause and double check here. Where's pause? I'm going to double check my calculation. Nope, makes sense, guys. Sorry, I was thinking in reverse. So when we picked 2, it gave us 0.25, which is just below what we needed. So we have to go down in number, because when you go up, when you raise a fraction to a higher power, it makes it smaller. So I was thinking in reverse. So no, we're doing okay. So if you got to that point, so I was correct in that. So this all makes sense. So when you get to here, you'd have to try it. So if you tried 2, you'd get 0.25. So then you'd have to try something less than 2. Usually you would think it'd be more than 2 because this is a bigger number, but when you're raising fractions to a power, the closer you are to 1, the higher the value will be. So that's why I got mixed up a little bit. So this is all correct in that way. Okay, so that's our examples. I'm going to stop there, and I'm going to put up some half-life type practice questions for you to work on as well. And then after that, we'll get into our next area, which gets into, we're getting close to, let's see, where are we here? After half-life, it will be, just got to get to my outline here. So, boy, this computer is slow. Yeah, so after our half-life questions, we did nuclear binding energy, we do nuclear fission and nuclear fusion, and we do nuclear equations, and then we'll talk a little bit about quantum physics, and that'll be it. So pretty short unit here. Okay, so I will post that up probably the next day, some half-life practice.